Myself, Dr. G. Venkat Subbareddy, Associate Professor of EEE Department. Today we are going to explain about stability in control systems. In stability in control system, there are two methods. One is nothing but a Routh-Hurwitz stability criterion. The second one is a determination of stability by using RH criteria and root locus technique in time domain analysis. Before going to discuss about Routh-Hurwitz stability criterion, then first of all, what is the stability in point of view control system? In control system point of view stability, what is the definition of stability? The gravitational force act restoring displacement ball to equilibrium position. That is nothing but a stable system. What is the stability? A system is defined to be asymptotically stable if its free vibration response approaches to zero as the time approaches to infinity. A system is considered to be unstable if the free vibration response growth without bounded as the time approaches to infinity. Finally, the system is said to be stable in control literature. It is a free vibration response neither decays or not grows, but remains constraints or and oscillations as time approach to input. Input is bounded, the output is also bounded. The system is stability. Otherwise, this is for a bounded input, the output is unbounded. The system is said to be unstable condition. These are some examples, some fixtures about stability. This cone, this is nothing but a stable condition. The second one is a neutral condition. This is unstable state. One is a stable condition, marginally stable, and another condition is unstable. In S-plane representation, the response of C of t with respect to time, that is the first one is a stable condition, the second one is a neutral or steady state condition, then the response C of t increases as time increases, then system goes to unstable condition. The stability in S-plane representation. What is using this concept, we can say this: whenever the system is stable, if the natural responses approaches to zero as the time is approaches to infinity, that is nothing but a stable condition. Unstable, which the natural response grows without bounded as time is approaches to infinity. Marginally stable, if the natural responses neither decays or nor goes, but the remaining constant or oscillates at time approaches to infinity. These are the definitions. The main definitions of the stability: the system is said to be stable if the following two conditions are satisfied. First condition is, when the system is excited by a bounded input, then the output should be bounded. This is the main definition of the stable condition, stability point of. When the system is excited by a bounded input or finite input, then the output should be also bounded, that is nothing but a finite. In the absence of input, the output towards tends to zero. These are the definition for stable condition. Why investigate the stability? Most important issues to design in a control system, that is important of investigate the stability. When unstable feedback system is of no practical values. A stable system should be exhibit a bounded output if the corresponding input is bounded. That is the most important issue is to design a control system. The stability is major role in the control system. In matter S-plane representation, when all the poles and zeros is present in the left half of the S-plane, the system is to be stable. According to the roots obtained by the characteristic equation, the denominator of a closed loop transfer function, when all the roots of the characteristic equation is present in the right half of the S-plane, the system is said to be the unstable condition. When all the roots are present in the left half of the S-plane, in the left half of the S-plane, the system is said to be stable. Whenever any one of the root is present in the right half of the S-plane, the system is said to be unstable condition. Then for finding the stability, for determining the open loop transfer function, First of all, to find out the open loop transfer function, then find the closed loop transfer function. The denominator of the characteristic equation, the denominator of the closed loop transfer function is nothing but a characteristic equation. When the roots of the characteristic equation is present in the left half of this plane, then the system is said to be stable condition. Otherwise, the system is unstable. Mathematical condition of stability: consider unity feedback system with the following open loop transfer function. G of s is nothing but a open loop transfer function. S k into k is a gain constant, ts plus 1, tas plus 1, tbs plus 1. This is nothing but the roots of the numerator will be zeros, the roots of the denominator will be poles. S power n is equal to number of poles are present in the origin that indicate the type of the system. This is zero type at first unit type 1 or type 2, that is n is depending upon the value of n. Ta, tb's are zeros and t1, t2 are poles. The denominator part of the characteristic equation of a closed loop system, that is nothing but a characteristic transfer function. The characteristic equation is nothing but the denominator of the closed loop transfer function is nothing but a characteristic equation. Mathematically, in general, the characteristic equation is given as q of s is equal to a0 s power n plus a1 s power n minus 1 plus a2 s power n minus 2 up to dash 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 a suffix n minus 1 into s power 1 a n is equal to 0. That is nothing but a characteristic equation. In case in this any one of the problem, when an open loop transfer function is given g of s, then find out 1 plus g of s into h of s is equal to 0. That is nothing but a characteristic equation. From this characteristic equation, we define as the system is stable or unstable condition. Mathematical condition for stability. Let's consider the characteristic equation. Q of s is equal to a0 s power n, a1 into s power n minus 1, a2 is s power n minus 2 up to dash 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 a suffix n minus 1 into s power n plus an is equal to 0. Then for finding the stability of the system, this is most important. First we find out the characteristic equation. Then from this characteristic equation, for the system is to be stable, the following condition must be satisfied. If the roots of the characteristic equation have a negative real part, then the system is said to be stable. Because the characteristic equation having a negative real part, then all the roots present in the left half of this plane, then the system is said to be stable condition. If any one of the root has a positive real part, repeated imaginary roots, then the system is said to be unstable. If any one of the roots is present in the right half of this plane or repeated roots are present in the j omega axis, then the system is said to be unstable condition. If the condition 1 is satisfied except the presence of non-repeated imaginary roots, then the system is said to be marginally stable or conditionally stable or limited stable. That is nothing but third condition. All the roots are present in the left half of this plane. That is, the roots having a negative real part. The system is stable. When the roots of the characteristic equation has a positive real parts, when all the roots are present in the right half of this plane, the system is unstable condition. Then all the roots must be present in the left half of this plane. Then non-repeated roots is present in the j omega axis. Then system is said to be conditionally stable or marginally stable or limitedly stable. These are the definitions of the stability by using this characteristic equation. For how to determine the stability? Find the roots of the characteristic equation, then observe the folds, that is the roots. First of all, find the characteristic equation. This is a procedure for determining the stability from given the characteristic equation. Find the roots of the given characteristic equation and observe the folds, that is the roots. If the folds are roots of a closed loop transfer function, this is important, not a open loop transfer function. This is a closed loop transfer function or in the left half of this plane that is having a negative real part, then the system is said to be stable condition. If the poles are roots of a closed loop transfer function in the right half of this plane, that is nothing but a positive real part, then the system is said to be unstable condition. The main difficulty in determining the stability, in which the increased order of the system, the number of roots determined is also increases. Next, one of the method to determine the stability, this is a very important method to determine the stability in a control system, is Routh-Hurwitz stability criterion or RH criterion. This method is based on ordering the coefficients of the characteristic equation into an array called Routh array. Then the coefficient of the characteristic equation is arranged in the Routh array, that is nothing but in array that is known as a Routh array. Using this method, we can tell how many closed loop poles or in the left half of this plane, that is a negative real roots, or in the right half of this plane, that is a positive real roots, or j omega axis. From this Routh-Hurwitz criterion, we determine that the number of roots is present in the left half of this plane, number of roots are present in the right half of this plane, number of roots is present on the j omega axis. This is a procedure for determining the stability by using Hurwitz criterion or Routh-Hurwitz stability criterion. This is Q of S is equal to A0 S power n, A1 S power n minus 1 and A2 S power n minus 2 up to dash 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 A suffix n minus 1 into S and An is equal to 0. Then in the first column, we find the column row, the highest power to the lowest power. That is nothing but S power n minus 1, S power n minus 2, S power n minus 3 up to dash dash. Last element is in the first column is nothing but S power 0. Then the coefficients can be written in the horizontally or row wise alternating value. S power n coefficient is A0, then we another S power n minus 2 is A2 and another one is fifth one is S power n minus 4 is nothing but A power n, like that. We arrange the alternative coefficients of S power n. The remaining coefficient A1, A3, A5, A7 like that. Then for remaining all the elements, all the rows must be calculated by using the formula. B1 is equal to, in diagonally, A1 A0 plus A0 A3 divided by A1. We get B1 value. Next, second one, A1 A4 minus A5 A3 divided by A1, then we get B2. Like that, we calculate all the rows of S power n minus 2, S power n minus 3 like this. Next, after calculating the row of B1 row, then calculate C1 row like that. B1 into A3 minus B2 into A1 divided by B1. We fill all the rows. In case of we find out the C2, B1 into A5 and B3 into A1 divided by B1, you get C2. Like that, we calculated remaining rows. Only 2 rows are filled by using the characteristic equation of the given characteristic equation. Then we calculate the S power n minus 2 row and S power n minus 3 row up to dash 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 S power n row. After filling all the elements in the Routh tabulation, then observe that all the elements in the first column of the Routh table has same sign. Then the system is said to be stable because all the elements is present in the left half of this plane. If any one of the sign changes in the first column of Routh tabulation, then the system is said to be stable. The number of sign changes in the first column that means the number of roots are present in the right half of this plane, then system is said to be stable. Only system is stable when all the coefficients in the first column of Routh tabulation must be positive, then the system is said to be stable condition. Generating array. How to array generating? First, label the rows with the powers of S from the highest power to power of S down toward the lowest power in vertical column. Next, form the first row of Routh tabulation using the even coefficients of the denominator of a closed loop transfer function of characteristic equation. Now form the second row of the Routh table using odd coefficients of the denominator of a closed loop transfer function. That is another row. The table is continued horizontally and vertically until the zeros are obtained. For convenience, any row can be multiplied or divided by the positive constant before the next row is completed without changing the values of the row below and disturb the properties of the Routh tabulation. This is a procedure for formulation of Routh tabulation. In the presence of, for generating Routh array, any missing terms are recording as zeros. If S power 2 terms is missing, then 0 into S square is written in the characteristic equation. Routh stability condition, RH criteria. What is the stability condition? For a system is to be stable, according to the Routh-Hurwitz criterion, it is necessary and sufficient that each term of the first column of the Routh tabulation must be positive. In this condition is not met, then the system is said to be unstable, and the number of sign changes indicates the number of positive roots. These are the theory about concept about Routh stability criterion. This is a very important concept while determining the stability in control system engineering, in control systems. Then we solve some problems on Routh tabulation. The first problem, for the stability of a continuous system having the characteristic equation, here S cubed plus 6s square plus 12s plus 8 is equal to simple characteristic equation. Then form the Routh tabulation. Highest power is S cubed, next S square, next S power 1 and S power 0. First row is coefficients of S cubed and S, another one is constant 1 comma 12 and even coefficients, then odd coefficients and even coefficients 6 comma 12 6 comma 8. The finding the remaining row S power 1 row and S power 0 we calculated by using the formulas. 6 into 12 minus 1 into 8 divided by 6, 64 by 6. The another one is 6 into 0, 1 into 0 by 6 is nothing but 0. 64 by 6 into 8 minus 6 into 0 divided by 64 by 8 we get it. In the first column all the elements must be positive, then the system is said to be stable condition. This characteristic equation is stable. Since there is no sign change in the first column of the Routh tabulation, it means that all the roots of the characteristic equation have a negative real parts and the system is said to be stable. When all the roots are present in the left half of this plane, then system is stable. This for example one is nothing but this system is stable condition. Another example, a simple example, S cubed plus S square plus 2S plus 24 is equal to 0. Routh array, S cubed coefficient is 1, S coefficient is 2 and S square coefficient is 1 and 24. Then formation of 22. 1 into 2 minus 24 divided by 1 we get minus 22 and this element is 0. By observing the first column there is minus 22. There are two sign changes because S2 coefficient is plus 1 and S power 1 coefficient, S coefficient is minus 22, plus to minus 1 change, minus to plus 1 change. Then in the first column one element is negative, then system is said to be stable. If you have two sign changes, then the two elements are two roots of the characteristic equation is present in the right half of this plane, the system is said to be unstable condition. Because there is a plus to minus, minus to plus, there is two sign changes, then the two roots are present in the right half of this plane, then system said to be unstable. Because two sign changes in the sign appear in the first column, we find out the two roots of the characteristic equation is present in the right half of this plane, then the system is said to be unstable condition. That is the second problem is unstable. The third, find the value of A. The system is stable. This is another example. Find the value of K. We find out the value of K, then the system is said to be stable. The system is stable condition. Then what is the range of K? Range of K. In a similar way, we find out the characteristic equation S cubed, S square, S and constant. S cubed, S square, S and constant. The coefficients of S cubed is 1. The coefficient of S is equal to 3. The another one is 0. S square coefficient 3 comma 1 plus K. Then find the remaining elements in the first row of Routh-Hurwitz criterion. 3 into 3 9 minus of 1 plus K plus 1 divided by 3 8 minus K by 3 comma 0. The another is 1 per K. In the first column all the elements must be positive. 8 minus K by 3 is greater than 0. 8 minus K is greater than 0. Then K is less than 8. 1 plus K is greater than 0, K is less than 1. Then the condition for stability, K range is equal to minus 1 less than K less than 8. Then the K value is within the region, then the system is said to be stable. Otherwise, system is unstable. Another problem, then given a unity feedback system. This is nothing but a unity feedback system. Then this is g of s, 1000 divided by s plus 2 into s plus 3 into s plus 1, that is nothing but g of s. H of s is equal to 1, h of s is equal to 1. Then first of all find the closed loop transfer function, that is c of s divided by r of s. Then g of s divided by 1 plus g of s into h of s. We get the characteristic equation s cubed plus 10s square plus 31s divided plus 1030, that is nothing but a characteristic equation. The denominator of the closed loop transfer function is nothing but a characteristic equation. From this characteristic equation, we prepare the Routh tabulation. From this Routh tabulation, we determine the system is stable or unstable condition. Such S cubed coefficient 1 comma 31, 1 comma 31, next to 10 comma 10,1030, then multiplied by divide by 10 1,103. Then find out the element in the first column of the Routh tabulation, that is minus 72 103. There is a two sign changes in the first column. One element is negative in the first column of the Routh tabulation, then system is said to be unstable condition when the two roots are present in the right half of this plane. In this example, the system is unstable. One more example. Find the stability of the system shown using the Routh stability criterion. This is the characteristic equation 2s power 4 plus s cubed plus 3s square plus 5s plus 10 is equal to 0. S power 4 coefficient 2 comma 3 comma 10, s cubed is 1 comma 3. Then calculate the remaining element in the first column of the Routh tabulation. S square coefficient is minus 7, s power 1 coefficient is minus 6.3, s power 0 coefficient is 10. Then there are two sign changes, plus to minus, minus to plus. Then the two roots are present in the right half of this plane. The system is also said to be unstable condition. The system is unstable because there is no there are two sign changes in the first column of the Routh tabulation, and the equation of the two roots are present in the right half of this plane. Then this system is also said to be unstable condition. This is one more example. Minus 12, there is two sign changes in the first column of the Routh tabulation, then system is said to be unstable. In a special case, there are two special cases for calculating of the Routh array in the first column. If any one of the element is appear in 0, that 0 can be replaced by epsilon. That is one method. The another method is all the elements in the any row will be 0. Then find out the auxiliary polynomial equation, that is the coefficients of the before the row, and find out the auxiliary coefficients. Then again go for Routh tabulation, then find out the system stable or unstable. There are two special cases. One special case is one of the element in the first column of the Routh tabulation is 0. How to calculate this? By using epsilon method. Two special cases can occur. Routh tabulation is 0 in the first column of the 0, then this problem here 0, then 0 can be replaced by epsilon. In the first element of the row is 0, division by 0 should becomes an infinity. To avoid this phenomena, epsilon, a small positive number, is assigned to replace the 0 in the first column. Then the value epsilon is allowed to approaches to 0, that is a positive value from the either the positive or negative side after the sign to enter the first column of determined. In this problem, for this example, s power 5, 2s power 4 plus 2s cube plus 4s square plus 11s plus 10. This is a characteristic equation. S power 4, 1 comma 2 comma 11. S for remaining 2 comma 4 comma 10. Then find out the first column. 2 into 2, 4. 4 into 1, 1 4 divided by 2, that is equal to 0. The first for calculating the Routh array, the first column of the row was 0. Then this 0 is replaced by epsilon. Epsilon is nothing but a positive real part. If the 0 appears in the first column of non-zero row of the Routh, replace with a small positive number epsilon, that is assume that positive. Then go for another, then find out the remaining values. Epsilon into 4 minus 12 divided by epsilon. This value is positive or not. Epsilon is a small positive value, then minus 12 divided by positive, then this is nothing but a minus 6. Then another one is a 6 comma 10. This is nothing but approaches to 6. Epsilon is greater less than 0, then minus 6. Two roots are present in the right half of this plane. The system is said to be unstable condition. In another example, 10 divided by s power 2s cube plus 2s power 4 plus 3s cube plus 6s square plus 5s plus 3. Then prepare the table. Then third element, s power 1 is 0. Then go for another, calculate the similar way. 6 epsilon minus 7 divided by epsilon is another one. Then find out the, if you choose the positive value, then two roots are negative real part, then system is said to be unstable. If you choose the positive, two sign changes, then the negative, there are also two sign changes. Hence the system is approaches to two poles in the right half of this plane. The system is said to be unstable condition. Only is nothing but whenever the element is present in the 0, that you can assume replaced by epsilon, which is nothing but a small positive value. That is one method. The another method is entire row is 0. For entire row is 0, then go for auxiliary polynomial equation and find out the derivation of the auxiliary polynomial that can be replaced by a original row, and proceed by the same process. Then we get this to determine the system is stable or not. This is nothing but a second row. Sometimes while making the Routh tabulation, we find that any entire row consists of zeros. This happened because an even polynomial that the factor of the original polynomial. In this case, must be handled differentially from the case of a 0 in only the first column of row. By observing this problem, S power 5, 7s square, 6s cubed plus 42s square plus 56. S cubed must be, all the elements must be 0. Then go for auxiliary polynomial. A of 7s power 4 plus 42s plus 56 is equal to 0. Go for, to solve this problem, go for polynomial equation 7s4. Take its derivative, 7s4 and take its derivative. Then derivatives are 4, 12, 0. Then replace that elements and go the same procedure. And 1, 1, 1, 3 and remaining are calculated. There is no sign changes. There is a no poles in the right half of this plane. The system is said to be stable. If all the element in the any row must be 0, then go for auxiliary polynomial, take its derivative and replace by 0 that coefficients, and the same procedure will be continued. In this example also, consider a control system have a closed loop transfer function g of s is equal to, this is nothing but a characteristic equation, s power for 1, 6, 8, and the row is equal to 0. Then find out the auxiliary polynomial equation s power 4 plus 6s plus 8. Then taking the derivative 4s cubed plus 12s plus 0, then replaced by 4, 12. And calculate the remaining, then calculate all the rows in the first column, 1, 1, 1, 3, 1 by 3, 8, all the elements must be positive, then the system is said to be stable. Then find the range of k. You have s power 4 plus s k plus s square, then epsilon c1, c1 is epsilon minus k divided by epsilon. Therefore, any value of k generating the 0, the system is unstable condition. This is one more example to determine the stability. Determine the stable and find out the range of k. That is equal to s k plus 2s square plus 4s plus k. S k would coefficient 1, 4, 2, k. Then calculate the remaining element. 2 into 4, 8 minus k divided by 2 and k. They find out that all the elements in the first column is assumed to be positive, then k is greater than 0. 8 minus k by 2 is greater than 0. K is less than 8. Then the stability condition is 0 less than k less than 8. Then only system is stable. Okay, this is completion of Routh stability criterion. What is the stability definition? How to find out the stability by using Harris criterion, and two special cases. Any one of the element is present in the first column of the Routh plane 0, that can be replaced by epsilon. When all the element in the first column is 0, that can be replaced by auxiliary polynomial equation. Then determine the derivatives of auxiliary polynomial and replace by the 0 row and go for RH criteria procedure. Then find out the stability. Okay, thank you.